Hi, good day. My name is Yesh Debidin, and these are my colleagues.
Chelsea Harrison.
Nixon Ramjan.
Keisha Douglas.
Together, we are Group 12, and we have been tasked by a recycling company to design a glass bottle pulverizer to produce cullets for use in recycling. Each member contributed different engineering aspects toward the success of the group. I contributed organizational and communicational skills, as well as critical thinking.
I contributed attention to detail, organization, and competency in design and editing software.
I contributed critical thinking and efficiency in SolidWorks.
I contributed research and competency in design and editing software.
Please enjoy our presentation.
We will now start our slideshow presentation, beginning with the background. Glass bottles have been around since 1500 BC, and it can still be seen today, only in a different form. Glass is the oldest type of packaging for soft drinks, fruit juices, and waters. Glass is non-porous and impermeable, so there are no interactions between the glass packaging and the products to affect the flavor of the food and beverages. Glass has an almost zero chemical state interactions, ensuring that the products inside a glass bottle keep their strength, aroma, and flavor. Glass is also 100% recyclable and can be recycled endlessly without loss in quality and purity. 80% of glass that is recovered can be made into new glass products by pulverization. Glass can be broken down into cullets, which is broken bits of glass of varying sizes. Cullets can also be used for producing recycled glass. The use of cullets in a glass furnace can significantly reduce the energy consumption in the furnace because the cullet has a lower melting energy requirement than the constituent raw materials. In addition to the energy savings, cullets reduce the amount of raw materials used. With the increase of glass bottle reuse, landfills will also be significantly alleviated, as they will not have glass bottles being used in landfills to take up most of the space.
Problem statement. As our landfills are becoming overly filled with waste that can be reused, a local recycling company has become extremely interested in recycling glass bottles. The company requires a device that can pulverize glass bottles collected and turn them into cullets that can be readily used for the production of new glass bottles. Project Aim. The aim of our project is to design a recycling machine that is capable of pulverizing glass bottles into cullets that can be used by the recycling company. Project Objectives. The objectives of our project are to conduct relevant literature and patent reviews to help achieve aim, to determine user-client requirements as well as key attributes and incorporate them into the design to carry out functions, to create varying conceptual designs encompassing the key attributes and select the most appropriate design that can best achieve the aim, to simulate the final design and make necessary improvements, and to create a prototype from the final design to show how the machine would function or look in reality.
And now we will go through the literature and patent reviews. In summary, it is seen that glass cullets have many uses, not only for the sole purpose of manufacturing recycled glass. It can be used in fiberglass manufacturing, abrasives, flux or binder in ceramics and bricks, filler in paint and plastic, filtration medium in swimming pools, frictionator in matches and ammunition, and also additive and flux in metal foundry. But however, there are also various disadvantages associated with cullets and its uses. For example, metallic impurities can cause significant refractory damage and shorten furnace life. Presence of ceramic will lead to quality problems. Organic content in cullet may lead to color and refining difficulties. Presence of aluminum in cullet may significantly reduce mechanical strength of end products, and impurities may give rise to undesired air emissions. We will now review the patents. As seen in the first patent review, this is a bottle crushing system for breaking glass bottles into smaller fragments. As seen in figure 8, there are two crushing jaws with a saw-toothed surface enclosed inside, as labeled numbers 26 and 29. The bottles are entered between these two jaws and are crushed by the pivoting of the jaw on the right-hand side. Directly below the exit of the two jaws are two tethered rolls which are attached to shafts to pulverize the broken up glass pieces. The glass enters the hopper into a crushing mechanism which shapes the glass. In the second patent review, glass bottles enter a chute leading to a rapidly rotating plate with veins formed at the upper surface of the plate, slope upwardly from the center as seen in figure 4. With the rapid rotation of these inclined veins, the glass bottles break up on initial impact. The glass is then fragmentized by repeated impact with the veins. The size of the pulverized glass is dependent on the speed of rotation and the time of operation, which can be controlled. The fractionalized fragments can then be controlled from a container at the bottom of the plate as they fall off from the peripheral edge as seen. Moving on to the third patent, glass bottles are fed into a similar chute system. Subsequently, glass breaks upon the impact with the grinding rotor with transverse blades as seen in figure 12, labeled as numbers 26 and 27. Glass fragments are then thrown against the grinding chamber wall, causing further pulverization and then falling into the lower section. The rotor impact blades force the smaller glass particles on the grinding grate blades and through the openings. Lastly, this bottle crushing system comprises of two sections, an upper and lower region. The upper component is the containing region where there is a drive present above the support panel separating the upper and lower region. The drive is connected to the rotating crushing element which is in the lower component, the glass receptacle region where it crushes the bottle upon impact. Glass bottles enter the system via a chute opening and discharges at the crushing element. There is a funnel chamber present within the system at an angle to enhance the retention of fragmented glass.
Client user requirements. The machine should be not too expensive to purchase, able to crush multiple bottles at one point in time, long-lasting and won't break easily, relatively easy to operate, and able to produce even grains of cullets. Design specifications. The machine should operate using 1 or 3 phase current supply, pulverize glass into cullets with grain size of 0.5 inch or smaller, include a fail-safe emergency stop, not require skilled workers to operate and crush a considerable amount of bottles in a short period of time. Key attributes: affordable cost, efficient, durable, user-friendly, and consistent. The metric table is ranked between 1 to 3, 1 being less favorable to occur and 3 being the most favorable to occur. For example, affordable costs will have a 1 under high cost and a low cost will be 3, which means low cost will be most favorable to occur. The pairwise comparison chart. This ranks the key attributes and assigns equivalent relative weighting. As you can see from the chart, efficiency has the highest weighting, therefore the most influential attribute. Functional analysis. This is based on input, processing, and output. Glass bottles, water, and air goes into the glass pulverizer machine and result in glass cullets, dirty water, dust, waste, noise, vibration, and heat. Functional decomposition chart. This is where the process is further broken down. Glass bottles are sorted by color using sensor technology. Labels are removed using water and then rinsed and further crushed, producing glass cullets. Functional means 3. Glass cullets. This is what are needed. This becomes our main function. Sorted, remove labels, rinse, crushed. This is things we do to achieve the glass cullets, which are called subfunctions. Enhanced pressurized water impact are methods to achieve the subfunctions, which are called means. The morphological chart. This shows the different options to achieve a specific action. For example, the action turn system on has 4 options: button, remote switch, voice control, and the person will choose the better option.
Concept 1. This is our first concept. It uses electrical energy and butters entered through the top. It pulverizes glass using rotating pins. The pins rotate within a mesh to produce a centrifugal force. The centrifugal force crushes the glass until it reaches the desired cullet size and passes through the mesh into a collection box. Concept 2. This concept is powered by electrical energy and comprises of a chute as well as 2 rotating shafts with extrusions. The butters enter via the chute and is grinded between the 2 rotating shafts to obtain the desired cullet size. The cullets produced are then collected below. Concept 3. Our third concept also uses electrical energy. The glass bottles enter the machine through an enclosed chute to be pulverized by a crusher. The crusher applies a force via an up and down motion produced by a reciprocating piston system to crush the glass. The glass is crushed until it reaches the desired size and passes through a mesh base to be collected below. It also incorporates a flywheel to make the crushing motion uniform.
Now we have a table of conceptual designs. This table compares the ways in which the actions are accomplished in the different concepts shown earlier. Now we have the design selection matrix table. What this table shows is the key attributes in which we have defined earlier and their relative weighting. All 3 concepts are shown as well too, and they're given raw scores of 1 to 3, with 3 being the best. So for each key attribute, the concepts are ranked. After they're given the raw score, they are multiplied by the relative weighting to give you a weighted score. At the end of everything, all the weighted scores for each concept are added up and totaled at the bottom. This helps us compare the scores of each of the concepts. Concept 3 had the greatest score with a value of 2.4, followed closely by Concept 2 with 2.08. Concept 1 got the lowest score of 1.52. So now we've arrived at our final concept. If you look at the diagram to the right, which is labeled, you can see that we have a conveyor, a crusher, and a grinder. We actually have seen the grinder and crusher earlier in concepts 2 and 3 respectively. We've decided to go with that because this will incorporate a 2-stage crushing process. Bottles would come along the conveyor and be crushed by the crusher and then get transported via the conveyor belt to the grinder, where the shards of glass would be grinded down into the final desired cullet size. A conveyor was chosen as it would decrease the time it would take to carry the broken bits of glass from the crusher to the grinder. If you look at the label diagram, you can see that a belt with separators travels along rollers. Close to the end, there's something called a crush plate. The crush plate is used to give support for when the crusher crushes the glass bottles on the belt. Here we have the crusher with the same core components from Concept 3. And finally, we have the grinder with the same core components from Concept number 2. This 2-stage crushing machine was chosen as the final concept as it will ensure consistency in the grain sizes of the cullets being produced by the machine. A conveyor was also used as it will increase the efficiency of the time it would take to transport the material from one crushing device to the other. We have reached the end of our presentation. Thank you for your time.